Hello class. This is section 16.1 on vector fields. So these two are examples of vector fields that we could see in real life. On the left, we have these wind speeds based around the San Francisco area at 6 p.m. As you can see, those different arrows indicating those vectors in the direction of the wind. And the one on the right are ocean currents off the coast of Nova Scotia. Again, those arrows dictating the direction of those currents. So we have two types of these vector fields that we can look at. The first one being a two-dimensional vector field. So if we let D be a set in R2, which is, also a point region like this picture I have here on the bottom right, a vector field on R2 is a function f that assigns to each point x and y in D a two-dimensional vector f of x and y. And we can write this with the component functions, also known as scalar fields, as f is equal to p times I plus q times j. So again, that I and j being those parts of the standard basis. And since we're in R2, we have two of those. So there's I and j both being vectors from the standard basis in R2. Standard basis in R2. And here to the right, again, I have that graph, just showing a couple of vectors mapped out onto it. We start at a point x and y and map the vector from that in the direction indicated by f of x and y. Likewise, a 3D vector field is very similar, only this one now is in 3D, so it's not just a point region. If we let E be a set in R3, a vector field in R3 is a function f that assigns to each point x, y, and z in E a three-dimensional vector f of x, y, and z. We can write this in the component functions, scalar fields, again with the standard basis now for 3 dimensions. F is equal to p times I plus q times j plus r times k. And again, this I, j, and k are the R3 standard basis. Again, this picture here on the right just showing a couple of points in that three-dimensional space and the vectors corresponding to f that map out from those. We also have a special type of a vector field, being this gradient fields, and we already saw gradients, right? Only now we are going to slightly change the idea of them. For a gradient vector field in R2, for example, we have a gradient of f of x and y. And as we saw when we took that gradient, we are taking the partial derivative of f with respect to x at x and y times I plus the partial derivative of f with respect to y of x and y times j. And in R3, that gradient adds that additional component of the partial derivative of f with respect to z, and all three of these are now at the point x, y, and z, and this last term being multiplied by k. And of course, if we had that in 3 dimensions. So for example, a vector field in R2 is defined by f of x and y is equal to y times I plus x times j. And we want to describe f by sketching 5 of its vectors. So I'm going to put here kind of a small table just so we can see this, what's going on. Of all the, a couple of points, And what happens from the function? So if we look at the point 1, comma 0, so I'm going to actually use a different color to denote this. There's our point. And popping it into the function that we have for this, we get a vector of 0, comma 1. So no change in x, but going up by 1 on the y-axis. So let me add an additional line here. So we can see where 1 is on the y. This would go up like that. If we choose another point, let us do 1, comma 1. This gives us a vector of, well, 1, comma 1. So at 1, 1, we have a point there. And again, we're going to add 1 to x and y. So graph a second point right there. Connect a vector like that. If we choose another one, let's do 1, comma 2. This would give us 2, comma 1 as our vector. So 1, comma 2, that would be there. And we want to add 2 to x, 1 to y. That next point is going to be, I need one more line. There we go. There. And connect that with a vector. And for 2 more, really quickly, let us do 0, comma negative 1 as a vector. That's going to give us negative 1, comma 0. So 0, negative 1 would be down here. And then negative 1, 0 is going to be there. So we have a vector pointing out like that. And just one more for us to see this. Let us do 3, comma 1. So as a vector, that's going to be 1, comma 3. So 3, comma 1 is going to be right there. And then 1, and then 3 will be all the way up there. Looks something like that. That's what that particular vector would look like. Another example of this one being for a gradient vector field, where our function f of x and y is equal to x plus y, that entire quantity squared. Right, so we had a formula for this. Let me draw the nebula for this, which is that upside down triangle from when we had the capital delta for this. F of x and y. And this is going to be taking the partial derivative with respect to x. This would be 2 times x plus y squared times I should probably put that in here. Plus, for the, no squared here in this. For the partial derivative with respect to y, that would be 2 times x plus y. And this one is times j. Since we are indeed in R2 for this. And again, I'm going to quickly sketch out a couple of these again, just so we can see it a bit in action. Let's do a point of 1, comma 1. Popping this in, we get 1 plus 1 made 2, and 2 times 2 made 4. So both of these components made 4 each. So our vector will be at 4, comma 4. So I need 1, 2, 3, 4 extra, and 1, 2, 3, and 4. So here's 1, 1. And you go to the right 4 and up 4. So something like that. Likewise, let's do 1, comma 0. Popping that in, we'll get 1 plus 0 made 1 times 2. So this will be a 2, comma 2 from both of those. So 1, comma 0 will be there. And then up 2 to the right 2, that'll be here. That will look like that in terms of that particular vector. And let's do one more of these. Let's do negative 2, comma 3. Adding those two together, that made a 1 times 2 from both of these. So this would also give us a vector of 2, comma 2. So I just need to add 2 extra lines there. A point would be 1, 2, 3 there. And for 2, comma 2, that would be there. So that vector will look something like that. So let me know if you have any questions or concerns. Thank you.